All right, so let's assume that you either fell asleep in class or, maybe you were actually absent. But let's talk about the circular motion lab results. Okay, so let's first talk about the graphs that we were trying to create. So the main graph was this guy here. Very exciting as it comes alive. Centripetal force versus velocity, or as we often said, speed, because we said those are kind of interchangeable in terms of conceptual elements. And if you did it correctly, you should have had this. All right, so you should have had a graph that looks like that. And then the next thing says, well, we want to linearize this. And so if you look, the centripetal force is moving up exponentially and velocity is moving linearly and basically reaching like an asymptote right here. So what we're going to do is we are going to linearize this. And what that means is we are going to end up making this curve into a line. So we have our centripetal force on that plane, and we're not going to mess with that because it's already exponential. But what we're going to do is we're going to take our speed and we are going to square it. And if we do this correctly, we basically get the following graph. Okay, so if you did this and it made it really bad, then I would double check your data, make sure that you had everything in the right planes, things like that. But let's label this correctly. Okay, so if we label this effectively, then we have a normal force up here, and we have its speed squared. So now we have meters per second quantity squared for our units. All right, cool. So now we have to ask ourselves, well, what do we get from this? So the first thing is if we look at our y-intercept, okay, our y-intercept tells us what y is when x is 0. Okay, remember, it's not like the automatic initial something. It's a huge mistake students make. They go, hey, it's the initial blah, blah, blah. All right, it's just what y is when x is 0. And so in this case, it's going to be what our centripetal force, or I should say our net centripetal force, is going to be when our speed squared is 0. So you kind of ask yourself, hey, if it's not moving in a circle, then is anything really happening? And so this kind of tells us that this y-intercept should be 0. Okay, you really should have a value that's very close to 0. It's going to have units of newtons, so it's like, hey, that kind of makes sense that there is 0 newtons, aka 0 force applied if you're not spinning something in a circle, because you then have no centripetal force. So it really should be 0. So hopefully when you did your lab data, your y-intercept value was very close to 0. And so we're going to end up dropping it. Okay, so we're going to drop it. It's going to go away. Will be dropped. All right. Now, if we look at the y-intercept, the slope though, that is a whole different story. All right, so let's bust out our slope evaluation. All right, now slope, it's always something constant. Something constant that will affect, maybe that's effect. I'm going to screw that up. I'm sorry. The results. Someone in the chat's going to yell at me because I used the wrong effect versus effect. All right, so here we go. Something that it's something constant that will affect your results. And specifically what I mean by results is the centripetal force. Now, if we go back to our thought process, we said that we were going to actually do 3 experiments. We said there were 3 things: centripetal force versus mass, centripetal force versus velocity or speed, and then centripetal force versus radius. Those were the 3 things that we thought would affect the centripetal force. We did a little discussion on it. We did some examples, and that's what we kind of walked away with. So in theory, we are going to be looking at the slope, and it really should kind of be like, something along these lines. Now, obviously, velocity is already taken because that's going to be on our x-axis. So maybe it's mass, maybe it's radius, who knows, maybe it's both. So now to kind of get a deeper analysis of this, we're going to break down the units. Okay, so let's look at the units that we have. And so the units for the slope were newtons per meter per second quantity squared. Well, those are not base units, so we're going to have to manipulate that a little bit more. Now, if we remember, a newton is a kilogram meter per second squared. And so if we then break up meters squared per second squared, some interesting things start to happen. So let's start crossing some things off the list. These seconds squared, they're going to cancel straight out. And then this singular mass is, meters is going to cancel out with the squared. So what we're left with are kilograms per meter. And that's really interesting because kilograms are units of mass. And meters would be units of our radius. So if we were to go into our data and you took the mass of your object and you divide it by the radius in meters, you really should get your slope value because the slope is actually telling us the mass of the object divided by the radius of the object. All right, so now we're going to go way over here now. So what this tells us is that we always start with y equals mx plus b. The y got replaced with our centripetal force. The slope we now know is replaced with mass divided by radius. And the x is our velocity squared. And then the b, we drop that because of what we talked about earlier. So this right here, this is our new equation. I'm going to rewrite it out in symbols only. So we're going to have centripetal force, and I'm going to do a little rearranging here. M v squared over r. Now the reason why I'm going to do a little bit of that rearranging is because this should look somewhat familiar. It should look a lot like sigma f equals ma. And the reason why it looks so familiar is because this right here is linked. So we also now have a stronger understanding of acceleration. So centripetal acceleration is v squared over r. And from our experiment, we knew that velocity by itself was distance over time, and distance of a circle is the circumference, so that's 2 pi r. And then we said the time was a special time. It was a capital T for period. And if we combine these two together, we take kind of this v and we slam it into here and square it, we actually get another way that we can write for centripetal acceleration. We can say AC is equal to 4 pi squared r over t squared. So we actually got a lot from this experiment, okay? So in recap, we linearized, we evaluated, we got the slope to be mass over radius, then we kind of manipulated that, we realized that centripetal acceleration was actually v squared over r, and if we combine that with the equation that we were using to calculate the velocity itself, we can get this other equation. So all of these right here are all potential equations that we could use in this unit. All right, so hopefully that'll help supplement those notes you had. And if you have any questions, you know where to find me. You guys have a great day and keep enjoying science.